Welcome back to elementary statistics. In this video, I wanted to talk about contingency tables. Previously, we talked about the chi-square test of goodness of fit to analyze how a observed frequency distribution compared to some expectation from a theoretical distribution or some other prediction of what would happen. In this video, we're going to extend that idea and allow ourselves to compare multiple frequency distributions. Things can get to be a little bit confusing in what we are doing here because it's hard to really understand, is the frequency distribution the thing that is appearing in the rows or in the columns? So for example, consider this frequency distribution in a contingency table. Where I am looking at 3 courses, algebra, statistics, and calculus, along with 3 instructors, Dr. E, Ms. N, and Mr. R. And each of these 3 instructors are each teaching a algebra class, a statistics class, and a calculus class. And we are comparing the enrollment in their respective classes. So Dr. E has 32 algebra students, 15 statistics students, and 16 calculus students. Ms. N has 28 algebra students, 31 statistics students, and 12 calculus students. Mr. R has 33 algebra students, 19 stats, and 15 in calculus. And so our question is, are these distributions the same? And again, the specifics of what that question is actually asking are not entirely clear. Am I asking, each of these instructors has the same distribution of students between their courses? Or am I asking, each of these courses has the same distribution of students between instructors? Am I learning English for the first time today? Anyway, those 2 questions, it turns out, are at their essence the same question. That is to say, the distribution between instructors for each course can be the same if and only if the distribution between courses for each instructor is also the same. So the relative frequency at which Dr. E gets algebra students compared to statistics compared to calculus is the same as the relative distribution that Ms. N gets between those courses and Mr. R gets between those courses. That can only happen if the distribution of algebra courses between these instructors, or students in statistics courses between these instructors, and students in calculus courses between these instructors follow the same ratios. So it's an all or nothing test. So it's hard to say which one we are analyzing because in a sense we are analyzing both. I'm going to go ahead and write down my hypothesis down here. The null hypothesis in this case is the claim We'll phrase it as students select these instructors in equal proportion for each class. And then the alternative hypothesis is going to be that there is a noticeable difference in the rate at which students select these instructors. And I'm also going to need a confidence level or a significance level. I'm going to use 95% confidence, alpha equals 0.05, which are equivalent statements. I use that in most of my videos, but it doesn't have to be the one you use. And I also need to calculate the degrees of freedom. The degrees of freedom in a goodness of fit, when we had one distribution among categories, was just the number of rows in the table minus 1. In our current table, we have rows and columns. So it's going to turn out that we are going to want to take the number of rows minus 1 and multiply by the number of columns minus 1. That is always the number of degrees of freedom. No matter what you are looking at, that's always going to be how it works. In our particular case here, there are 3 rows, there are 3 columns. So the degrees of freedom here is 4. 4 degrees of freedom is something that tends to come up. It's a nice balance point between there's enough here to make things interesting and there's not too much to make things challenging. So you'll see a lot of examples in homework and in practice problems that involve 4 degrees of freedom, sometimes 3, sometimes 5, sometimes 6, rarely different from that in these problems just because it gets too messy too quickly. Right, but we can look up in the chi-square distribution and find that the critical value of chi squared at 4 degrees of freedom and alpha equals 0.05 is 9.488. It's a convenient number that we've used in the past by coincidence, and so that's pretty easy to work with again. Now to perform our calculations, I'm going to scroll back up to the table that I've been working with, where I listed things out. I'm going to introduce an extra row called the total and an extra column called the total. And I'm going to say that backwards because I'm not paying enough attention to what I'm doing. I apologize for that. That's confusion that is completely unnecessary, but we'll deal with it. Extra row of total, extra column of total. And we're going to total each of the columns in the bottom row. We're going to total each of the rows in the bottom column, or in the right column. Words and me today, not getting along. I apologize. Right. Anyway, 32 plus 28 plus 33 comes out at 93. 15 and 31 and 19 comes out at 65. 16 and 12 and 15 comes out at 43. And then the rows. 32 and 15 and 16 comes out at 63. 28 and 31 and 12 comes out at 71. 33 and 19 and 15 comes out at 67. All right. Going column by column, we can see that the total values in these columns are quite a bit different. There are more students taking algebra than statistics and more students taking statistics than calculus. Unfortunately, a reality of our world. But looking row by row, we see that the numbers are relatively consistent. There are approximately equal numbers taking Dr. E, Ms. N, and Mr. R. But no matter which way you go about it, this last row, last column, well, if I add 63 plus 71 plus 67, adding down that column, I get 201. If I add across 93 plus 65 plus 43, I also get 201. That's a nice double check. The number in the bottom corner here should be the grand total, the number of things in the table in its entirety. And it doesn't matter if you add in rows and then add the columns together, or add all the columns and then add that row together. It will get you the same value. All right. I'm going to now copy this entire table, although you're going to see when I paste it that I'm actually going to get rid of a lot of information. Actually, so that I don't have to scroll quite so far, let's paste it twice. That one is just for reference. We'll come back to it. Take advantage of the fact that I can annotate things easily and shrink that down a little bit. Might be a little bit hard to read, but the numbers are there, and that's going to be what matters. And then let's get one more table here. This is going to be the one that we're working with. And in this table in the middle, I'm going to get rid of all of the original data, leaving the totals. This is going to be my table for the expected value. And to find the expected value of each entry, I'm going to multiply the total for the row times the total for the column divided by the grand total. Let me write that out for one example first, and then let's talk about why we choose that value. So Dr. E and algebra. The total on this row is 63. The total on this column is 93. And the grand total is 201. My calculator tells me that 63 times 93 divided by 201 comes out at around 29, give or take a little bit. Now, I want to think about that in terms of proportions. If I took just the row 63 divided by 201, all right, so just this much of the calculation, that is the portion of the total, the percent of the total population that took Dr. E. If I multiply that by 93, that will give me the fraction, instead of as a percent, that will turn it into a portion of those 93 students who took algebra. So the percentage of students who took Dr. E multiplied by the total number of students who took algebra gives us the expected number of students who took algebra, 29 in this case. And I'm going to kind of go diagonal to show off all of the different things that we're going to be looking at value-wise. Ms. N, there were 71 students who took Ms. N. There were 93 students who took algebra. Multiply those together, divide by 201 total students in the survey. And get something on the ballpark of 33 students right here. And then we'll have 67 times 93 divided by 201, which comes out at 31. I'm not going to write out the calculations for all of these because I don't quite have enough room. But let's take a look at just one more here. 65, writing this in the other order, sorry about that. 63 students who took Dr. E times 65 students who took statistics divided by 201 total students gives us an expectation of 20 students taking Dr. E for statistics. Expectation of 23 students taking Ms. N for statistics. And then if I take 67 times 65 divided by 201, comes out at about 22 students taking Mr. R. 63 times 43 divided by 201 is about 13 students taking Dr. E for calculus. 71 times 43 divided by 201 is 15 students taking Ms. N for calculus, and 67 times 43 divided by 201 is an expectation of about 14 students taking Mr. R for calculus. All right. Now that we have that, I'm going to shrink that one down a bit as well because I have a lot of information here and it's not nearly everything that I need. In total, I want to take the sum of the observed minus expected squared divided by the expected. So taking Dr. E for algebra, the observed was 32 and the expected was 29. (32 minus 29 is 3. 3 squared is 9. And 9 divided by 29 is something on the ballpark of 0.310. That's the number of decimal points we have for our comparison, so that's a good place to round. Then I will compare 28 to 33. I get 0.758. Compare 33 to 31. So it's 33 minus 31, which is 2. Square that is 4. 4 divided by 31 comes out at 0.129. Right, go on to statistics. Compare 15 to 20. 15 minus 20 is -5. -5 squared is 25. 25 divided by 20 is 1.25. 31 minus 23 is 8. 8 squared is 64. 64 divided by 23 is 2.783. Continuing onward, Mr. R for statistics, 0.409. Then for calculus, Dr. E, 0.692. Ms. N, 0.600. Mr. R, 0.071. That gives us all of these O minus E squared terms. I want to add all of those together to get our chi-squared value. Numbers are ugly enough, it might be worth adding them together twice, but I do get 7.002. Right, so I got chi-squared is 7.002, and 7.002 is less than the critical chi-squared value we wrote down earlier, 9.488. And that tells us that we want to accept the null hypothesis. There is no evidence of a difference. That's not to say, as I write this down to be clear, I wrote down that there is no evidence of a difference in the rate at which students register for these instructors. That's not to say that there's no evidence in the rate at which students register for individual classes. That's not to say that there is no evidence of a difference in the total registration for each instructor. What I'm saying, what I am claiming here is that with the information that we were able to analyze, the course doesn't make a difference in the rate at which students register for the instructor. All right. It's a little bit messy. Trying to keep everything straight in contingency tables is less than pleasant. And the limitations of working on this screen limit things even further. So it makes it a little bit hard to follow along. I will tell you that one of the things that I like to do when I have more writing space, when I'm in front of a classroom and I have a large chalkboard to work with, or even when I'm at my own work and I have plenty of paper, I will write out the entire contingency table for the observation. I'll write out the entire contingency table for the observation. I'll then write out a new contingency table for the difference, O minus E. I'll write out a new contingency table squaring that, and yet another new contingency table dividing by E. I can't really do that with what we have on the screen because it requires referencing back and forth to too many different tables, and they just don't all fit. So trying to follow along here is a little bit messy. We had to rely a lot more on writing things out algebraically rather than writing things out statistically. But there's my piece of advice for you. As you're working on these, don't be afraid to write out the table over and over and over again. Write out your O table, write out your E table, write out your O minus E table, your O minus E squared table, and your O minus E squared divided by E table. And then you have this one table that has all of the data points. You won't get lost trying to remember what you were working on last time, which ones you finished, which ones you haven't. It's all there and organized. Then add everything up and go from there. That's all I have on this video. As always, thanks for joining me. I'll see you next time.